In this video, you will learn how to identify oxidation-reduction reactions. These are also known as redox reactions. The steps that you'll need to do, so the how here, step 1 will be to assign oxidation numbers to every element. And then step 2, check to see if oxidation numbers changed during the reaction. In a redox reaction, it's required that electrons are transferred in order for it to be redox. So when we look to see if any of the oxidation numbers have changed, what we're really looking for is checking to see if electrons were transferred. So the oxidation number, I'll give you a definition here. Oxidation number is the charge each atom in a molecule would possess if it were ionic. And it's just one of the several ways we'll talk about accounting for electrons in a molecule and within a reaction in this class. So what I'm going to do is I'm actually going to pause. I'm going to fill out some rules for assigning oxidation numbers, and then we're going to go through these and do some practice examples. All right, so we're going to start with most of the rules are out here, but don't worry, we're going to go through and I'm going to give you some examples. So these rules for assigning oxidation numbers need to be followed in order. And this is very important. So follow these rules in order as you go through. So the first rule is that free elements have an oxidation number of 0. So what we mean by this is that if you had solid copper metal, that copper would have an oxidation number of 0. If you had Cl2, which is how chlorine is found as a pure element, the oxidation number here is 0, and so on. Number 2, a monoatomic ion, the oxidation number for that atom, since it's monoatomic, is equal to its charge. So calcium 2 plus has an oxidation number of +2. Cl minus has an oxidation number of -1, etc. For rule number 3, it says the numbers sum to the overall charge on a molecule. So I'm going to look at 2 examples here. So first of all, if we were talking about something like water, which is neutral, it means that 2 times the hydrogen oxidation number plus 1 times the oxygen oxidation number has to add up to 0, because as a molecule, it's a neutral molecule. If you had an anion, like nitrate, 1 times the nitrogen oxidation number plus 3 times the oxygen oxidation number equals -1. So the whole molecule has a -1 charge, so everything has to add up to -1. Rule 4, metals have positive oxidation numbers. And some specific examples here, everything in group 1 will have a +1 oxidation number. Everything in group 2 will have a +2 oxidation number. And this will end up being easier to remember than you might expect, because this is just like when they're in ionic compounds. The nonmetals, so we've covered everything up through metals. So nonmetals, again, these go in priority order. So fluorine gets a -1. Hydrogen gets a +1. Oxygen gets a -2. And then everything in group 17. So fluorine is in group 17, but fluorine is considered by itself first, and then everything else in group 17 later gets a -1. Group 16, these get a -2. And then group 15, they get a -3. And after all of this, we haven't covered every single possibility in the periodic table, but anything that's left over, you will be able to fill those in with rule number 3. So anything that we didn't explicitly cover in all of the other rules will you'll be able to get the oxidation number with essentially a process of elimination. Okay, so once you have oxidation numbers for everything, we're looking to see if the oxidation numbers for a specific element change as the reaction happens. And in that reaction, if an element's oxidation number increased, this means that it lost electrons and was oxidized. And if an element's oxidation number decreased, it gained electrons and was reduced. So within a reaction, you will be able to look at these numbers, identify what was oxidized and what was reduced. And if you have one and you have a full reaction, you should also have the other, because these electrons that are being moved around are not explicitly written if we have a full reaction. We'll see them when we do something called half reactions, but not in the full. So, of course, this has some acronyms to help you remember it. Whichever one works for you, I'm going to give you a couple that are really popular. So one is that Leo says GER for losing electrons oxidation. And on the other side, gaining electrons reduction. Or, if you like, there's another one that is oil rig for oxidation is loss of electrons, and reduction is gain of electrons. Now, to complicate this a little bit further, we also, as chemists, like to call things oxidizing agents and reducing agents. So An oxidizing agent is the thing that is reduced. So my recommendation for remembering this, clearly it's the thing that is reduced is the oxidizing agent. So there's that opposite thing going on there. But if something is being reduced, we call it the oxidizing agent because it's causing the oxidation of something else. So the thing that is reduced, instead of, it's the same thing, but if it helps, instead of saying oxidizing agent, you can say agent of oxidation. Just in your head to help you keep it straight. So the oxidizing agent is reduced, which means the thing that is oxidized is causing reduction. So the reducing agent is oxidized. So it is the agent of reduction, if you will. So let's practice with this. So the question is this a redox reaction? And I have two examples. One, this says 2HCl aqueous plus magnesium solid turns into H2 gas and MgCl2 aqueous. All right. So oxidation numbers, right away, just from rule 1, a free element is 0. So magnesium solid is 0. Hydrogen gas is 0. I think that covers everything that we can. I don't have any monoatomic ions. We'll come back and use rule 3 in a little bit. The next rule that I get to is that metals have positive oxidation numbers. So magnesium is a group 2 metal, so it has a +2. And then I don't have anything else. So then the nonmetals in order, I don't have any fluorines. I do have hydrogen, so this hydrogen is going to be a +1. And then I think I can do rule 3 for everything else. So in HCl, that overall molecule is neutral. So if hydrogen is +1, chlorine has to be -1. And in MgCl2, this is an ionic compound that we can recognize at this point. If magnesium is plus, then each chlorine is a -1. Okay. So then I look at the oxidation numbers. What do we have? Chlorine is -1 on the left and -1 on the right. So chlorine doesn't change. The magnesium goes from 0 to +2. So it lost electrons. So it was oxidized. So magnesium was oxidized, which means it was the reducing agent. And hydrogen, it's the only thing I haven't accounted for, goes from a +1 to 0. So it gained electrons. So it had to be reduced. Hydrogen was reduced. So it was the oxidizing agent. All right, one more example. Again, the question is it redox? I'll number it since I did the other one, number 2. So this is HCl aqueous plus silver nitrate, also aqueous, turning into HNO3 and AgCl. All right. Don't have any free elements. I don't have any monoatomic ions. I don't have any group 1 or 2 metals that fit. So the nonmetals, the hydrogen is a +1, and it looks like it's the first piece of information I have for the HNO3 on the right as well. After that, oxygen is the next thing. So -2 on my HNO3. This is kind of odd, right? I don't have rules for silver, but also I have my nitrogen falls pretty low in my priority. So sometimes the best thing that you can do is split these up into ions that you know. So like the silver nitrate, I know is silver 1+ and NO3-. And I mean, my HNO3, right, is an H+ and an NO3-. And my silver chloride over here is going to be an Ag+ and a Cl-. Those won't be as important to have pulled apart, but the silver nitrate is going to help us immensely just by splitting it into things that we already know, even though it's not explicitly related to checking the oxidation numbers. Okay, so let's try going through this now. So the HCl, if it's a +1 for the H, it's got to be a -1 for the Cl. My silver nitrate, now this silver is a monoatomic ion, that's a +1. In my nitrate, I have to go into rule 5. All of my oxygens will be -2, which means in order for nitrate to have an overall minus charge, it's whatever nitrogen is plus 3 times -2 equals -1. So nitrogen has to be a +5. And in HNO3, hydrogen is +1 again. The oxygen is still -2. So just like in nitrate before, the nitrogen has to be a +5. Then silver is +1 and chlorine is -1. And where this leaves me, my H's are the same, my Cl's are the same, silver's the same, nitrogen same, oxygen same. This just ended up being a reaction that was not redox. And the way that we checked that was checking to see if the oxidation numbers had changed.